Hello guys, today let's go over AP Physics C, Electricity and Magnetism 2021 FRQ. The first question, there's three questions. The first question is about the circuit. There's a circuit shown above. We have an ideal 10 volts battery here. EMF is equal to 10 volts. We have three different resistors. We have three different capacitors. They all have different either resistance or capacitance. And there's an open switch S here, and the capacitors are initially charged. Now switch S is closed. So we need to calculate the current through R1 immediately after switch is closed. So because these these capacitors are uncharged, so they all behave as like the connected wire, so we can simply ignore them. So by using Kirchhoff loop rule, if we start from the positive side of battery, go through R1, and we can go through, you can go this side or this side, because as I said, they are not charged, so they behave like connected wire, and they go like this and back to the battery. So basically, through the entire loop, only pass through R1. Therefore, EMF minus I times R1 is equal to what? Is equal to 0, right? So R1 should equal to EMF, and I should equal to R1 should equal to, EMF, which is EMF divided by R1, which is 10 volts, divided by 100 ohms, which is equal to 0.1 amps. Okay, part B. Now switch S has been closed for a long time, and the circuit has reached a steady state. Okay, so it has been closed for a long time. There's no current in this side, in this wire and that wire. So current only flows from the battery and goes from R1, the wire with R2, and the wire with R3, and then back to the battery here. So we can, what we can do here, because R2 and R3 are parallel, so basically we can just simply, make R2 and R3 equivalent resistor. We call it REQ1. REQ1 because R2 and R3 are parallel. Therefore, REQ1 is simply 1 over R2 plus 1 over R3, and their sum to -1th power. So REQ1 should be 1 over 30 plus 1 over 60 ohms to -1th power. We can plug in them into calculator here. It should be 20. It's 20 ohms. Let's combine REQ1 and R1. REQ1 is here. The current goes from R1 then to REQ1. We can make them REQ2, REQ1 and R1, REQ2. Since they are in series, we just need to sum it up. So REQ2 just R1 plus REQ1, which is equal to 100 ohms plus 20 ohms, which is 120 ohms. Therefore, the current passed through the equivalent REQ2 should be IEQ2 equal to 10 volts divided by REQ2, which is 10 volts divided by 120 ohms, which is about like 0.083 amps. Now we need to calculate potential difference only through R1. Therefore, the potential difference delta V1 is equal to I times R1, which is 0.083 0.083 amps times 100 ohms, and that is equal to, well, that should be definitely 8.3 volts. Okay. Part C, part 1 for part C. Calculate the charge stored in positive plate of capacitor C2. So now let's take a look at C1 and C2 now. Well, we have known that based on Kirchhoff loop rule, EMF minus delta V1 minus the potential difference across these two capacitors should be 0, right? So we call them EQ1, CEQ1. So minus Q divided by CEQ1 is 0. And we know Q, well, Q is the total charge stored on C1 and C2. And on each side, on each capacitor, on each C1 or C2, the Q is also Q. The charge stored on C1 is Q, on C2 is Q. Total charge still Q, right? Because they're in series. So we can calculate CEQ1 first. CEQ1 should be 1 over C1 plus 1 over C2 to negative 1th power. Just plug into calculator. Not going to write them. Well, it should be 6. Okay, should be 6. 6 microfarads. And EMF minus delta V1 should equal to 10 minus delta V1 is here is 8.3, so it's 10 minus 8.3, right, which is 1.7 volts. So Q should equal to, well, CEQ1 multiply by EMF minus delta V1, which is equal to 6 microfarads times 1.7 volts. That should be 1.10.2. We have a microfarads here, so it should be microcoulombs. Okay. Part 2 is the charge stored on capacitor C3 greater than, less than, or equal to the charge stored on capacitor C2? Well, definitely greater than. Right? We can do some analysis here. So we know that C3 is 20 microfarads, right? The charge stored on C2 is Q. And Q divided by CEQ1 is the potential difference here. And Q, we call Q3, the charge stored on C3 we call Q3. Q3 divided by C3 is a potential difference here across C3. If we start from the battery, we can go to R1 first, then go to the equivalent capacitor CEQ1, and then go back to the battery. But we can also have another path, go to R1, and we go directly to C3, and then go back to the battery. That means the potential difference across, well, C3 and across CEQ1 should be the same. That means these should be equal to each other. As we know, since CEQ1 is we have 6 microfarads, which is less than C3, right? Which is less equal to 20 microfarads. Right, since CEQ1 is less than CEQ3, that means Q3 should be greater than Q, such that the ratio can remain the same, right? So the potential difference can be the same. So it should be greater than. All right. Next part. Now switch S is then opened. Well, when switch S is opened, the battery stopped working because there's no connected loop. and these capacitors have been charged. Therefore, they start releasing their energy, right? There's a current in these small loops. And the first question asks us to determine the current through R1 immediately after switch is opened. Well, is that possible to form a loop through R1 when the switch is open? Well, definitely impossible, right? First, battery doesn't work, as we said before. It's also impossible for these capacitors to release their energy through R1 and then form a loop, because you have to pass the switch. Therefore, the current through R1 is 0 amps. Or you don't need to write amps, because 0 is 0, just nothing. And for part 2, calculate the current through R2 immediately. Of course, we can form a loop with R2. So that's the question, right? How do we know the current through R2? Well, don't forget, in the previous question here, right, we have determined in part 2, in part C, part 2, I've told you guys that we can form a loop, either use CEQ1 or C3. Take CEQ1, for example. The potential difference across here, right, should equal to EMF minus delta V1, which is 1.7. So we know the potential difference for CEQ1, which is equal to the potential difference through C3, is equal to EMF minus delta V1, which is 1.7 volts. And we can see the C3 and R2 can form a loop, right? So that means delta V C3 minus the delta V across R2, well, we can call it I would call I2 times R2 should equal 0. Therefore, I2 should equal to delta VC3 divided by R2, which is equal to 1.7 volts divided by R2 is 30, so 30 ohms, which is equal to, logging to calculator, should be 0.057 amps. Okay, and E, on the axis below, a graph of potential difference V across capacitor C2 as a function of time t. Its switch is opened at time equal to 0. Label the maximum value here. So here we need to find the maximum value for the potential difference across only C2, not CEQ1. We have known that the potential the charge on the C2 is 10.2 microcoulombs. So delta V C2 should be Q2 minus C2. That is equal to 10.2 microcoulombs divided by we have 15 microfarads for C2. That should be 0.2 divided by 15. It should be 0.68. It'll probably be 0.67 or even 0.69, but it doesn't matter. So it's 0.68 volts here. It's volts. Micro cancel. So it's coulomb or farads volts. And it should draw something like that. It should be an exponential decay. Exponential decay. Okay. Capacitor C3 is now replaced by two 10 microfarads capacitor connecting series in series. That's very important. Switch S is now closed and the circuit reaches equilibrium. Switch S is then open at time equals 0. For time greater than 0, we'll sketch off a graph for new voltage across C2 as a function of time be above, below, or the same as the sketch for part E. We know that CEQ, I would call CEQ2, right? CEQ2 is CEQ1 here and C3. Well, before that, the equivalent capacitance is because they are parallel to each other, right? We see Q1 plus C3. If C3 is less, right? We know the C3 is replaced by two 10 microfarad capacitors, so C3 new should equal to 10 microfarads, so it's 1 over 10 microfarads plus 1 over 10 microfarads connected to first 1th power, so should be 5 microfarads, which is less than C3, which is equal to 20 microfarads. If C3 is less, the final equivalent capacitance of all capacitors is less than before. And since V is equal to V naught times e to negative t divided by r times CEQ, right? We know CEQ is less. If CEQ is smaller, 1 over r CEQ will be greater. So the graph, so the voltage, or the potential difference I'm gonna write it here, like decreases the, I should not write outside the box, but decreases more quickly. So it should be below. So it's below. All right, let's get into the next question, which is Q2. Q2's, oh, it's a really interesting one. We have the electric balance here. Well, basically measure the weight of the conducting sphere, the lower one. Remember the sphere is conducting, that's very important. The charge can freely move on or inside the sphere. The student perform experiment to study the force between two charged objects pairs as shown above, containing two identical conducting spheres. The upper sphere attached to an insulating string, which can be used to move the sphere downward. The lower sit on the insulating rod, which can electronic balance 0 before the lower sphere there. Okay, for the first trial, a charge of Q is placed on each sphere, and then upper sphere is slowly moved downward here. So at the same charge and on both spheres and pushing downward, we record data. Y-axis is F, the force measured by the balance. You need to remember that the balance also measure the weight of the sphere, so you need to remember that. And y-axis is 1 over d squared. D is the distance between the center of two spheres. Draw a line that represents the best fit when shown. So let's draw a line of the best fit here. Well, we can draw like this, right? We can draw like this. It's like, okay, that looks good. Let's draw it. Okay, that looks good. You take 2 points, use this graph to calculate a charge Q. We know F should equal to KQ times 1 over d squared. Okay, so that means this is Y, KQ is M, this is X. You can calculate the slope, which is KQ. So KQ, which is the slope. Well, although it measured the force, but force will not change with the weight. I mean the weight of the sphere, but it doesn't matter because as you move downwards, the additional force is only contributed by the electric charges. It's only electric forces. So when you calculate the slope, you don't need to care about that. So let's take 2 points. The first point I would take probably here, like somewhere here, like here. So if this is 10, that should be 5. So this point is 5 and 9,000, but in micronewtons. Another point I would pick would be somewhere here actually. This is 90, so this is 95 and 13,000. So I will say should be changing y over changing x. Right, so it's changing y is like that. It should be something like that. So plugging into a calculator first. 90, like 44 point, like 44 micronewtons times meter square, which is, well, because we are in meter square, we can convert, we're in meter square and micronewton, so we need to divide it by, divided by 10 to the, how many power? This is micro, so 6 power. So it's about 4.44 times 10 to negative 5 Newton meter square. That means we know what K is, right? So we can easily calculate the value for K. You should just simply divide this by, for Q, divide this by Q, divide this by K. K is 9.00. What K is, let's check. If you have the formula sheet, better take it out. Formula sheet says that K, well, should be, find the formula sheet, formula sheet should be here. Yeah, I found it. Formula sheet. It says that K is 9.0 times 10 to it's 9.0 times 10 to the 9th newtons meter square per coulomb. So let's do the division. Divided by 9 times 10 to 9th power should be 4. Should be like 4.9 times 10 negative 15 coulombs, which is about, well, just in coulombs. I think that's okay. All right, let's get into the next question. Determine the distance. Determine the distance. Okay, on the graph of the previous page, draw a circle around the data point that's taken when the distance between the centers of spheres was the least. Because this graph was in 1 over d. So we need to draw the highest point, the greatest point, which is this one. and determine the distance between the center of sphere for the data point in decay above. This point is, the distance is 80, well here is 85 for this line, so this one is in the middle of between 80 and 85, which is 82.5. So the distance is, so we know 1 over d squared is 82.5 1 over meter squared. That means d is equal to square root of 1 over 2.5 meters squared meters. That is equal to 0.11 meters. What's the physical quantity does the vertical intercept represent, or the y-intercept? As we mentioned above, we mentioned before, electronic balance also measures the weight, the mass of the conducting sphere. So you can say that when they are infinitely far away, there's no force on there's no electric force on the sphere, so it's only the weight. So it should, so it measures, so it does represent the mass or the weight, you can say the weight or the weight of, well, probably more accurately, you can say the weight or the gravitation, the gravity on, let's just say the weight of the apparatus on the lower sphere, right? Just find answer when the square, which is 0, the electric force reaches 0 when two spheres are infinitely apart. So there is no contribution from electrical force. Electric force, probably electric force. Okay, the experiment extended by collecting additional data points which appear on the right side of the graph shown above. The new data points do not follow the linear pattern seen with the first points. The group of students tries to explain this discrepancy. One student says that charges leaking off the top sphere. Could this explain the discrepancy? Of course, yes, because when charge is leaking, as F is equal to KQ divided by D squared. If Q is decreasing, force should also be decreasing, right? So let's make this graph non-linear here. Definitely yes. On the circle representing the spheres below, use plus sign on each sphere to represent the location of highest concentration of excess positive charge. Of course, it should repel to each other because both are positive. Spin rearrangement could be responsible for discrepancy. Well, to excess positive charge repel to each other So they are like further apart. So D increases, F, which is equal to KQ over D squared, decreases. A third student suggests that the experiment should be modified so that decreases, right? So one thing to mention, when they're getting closer, they move further apart, right? So one thing to write, so when getting closer, well, I would say when two spheres getting closer. Okay. The circles representing the sphere below use a plus sign at the bottom sphere to represent location of the negative sign top, so the charge on top becomes negative. They should attract to each other, so it should be like this. For separation distance equal to data to point 2, would the magnitude of force reading with sphere charges be greater than, less than, or equal to the magnitude of force reading? Be greater than, because positive and negative charge attract to each other. So the distance between charges on two spheres is less. So d1 squared increases. So F equal to KQ over D squared increases. So it should be greater. Okay, we need to be quick. Last question. A thin conducting ring area A and resistance R is aligned in a uniform magnetic field directed to the right perpendicular to the plane of the ring as shown. At time equals 0, the magnitude of magnetic field is B naught. At t equals 1 second, the magnitude of the magnetic field begins to decrease according to the equation BT equal to beta over T, where beta has units of Tesla times seconds. A, derive the equation for the magnitude of induced current in the ring as function of T for T greater than 1 second. Express your answer in terms of beta, A, R, T, and physical constant as appropriate. So we know since it's exactly perpendicular here, so basically the magnetic flux across the ring, across the surface formed by the ring is B times A times cosine 0 degrees, right? Because we have this vector here. It should be 0 degrees, which is equal to B times A. And EMF is basically negative D over dt time of B times A, and B is beta over T, so it's negative beta times A divided by T. That is equal to beta over A divided by T squared, right? If you use power rule to do this. And that's just simply EMF. If you want to get the current I, you should use EMF to divided by the resistance, which is equal to beta times A divided by R times T squared. That's the answer for part A. Now assume A is 0.5 meters squared, R is 2.0 ohms, and beta is 0.5 Tesla per times seconds. calculate the electrical energy dissipated in the range from t1 second to 2 seconds here. Let's say we know the power should equal to I times delta V. In this case, it's EMF, which is equal to current. I is current, so it's beta times A divided by R times T squared. EMF beta times A divided by T squared. So power is beta squared, A squared, divided by R times T to the 4th power. And the electrical energy dissipated should be the integral from 1 to 2 delta E 1 to 2 of beta squared A squared divided by R times T squared d to the 4th power dt. Well, t to the 4th power is 1 over t to the 4th power, basically t to the negative 4th power. If we integrate, it becomes t to the negative 3 power divided by negative 3. So it should be negative beta squared A squared divided by 3R times 1 over t to the 3rd power from 1 to 2, which is, plugging into calculator here, should be 3R. That is 1 over 8 minus 1. And plugging these values into here, negative beta is 0.5 squared times A is 0.5 squared times 1 over 8 minus 1. We divided by 3R, R is 2. So that should be, well, should be about like 0.0091 joules. I guess it's right. And the next part, question 3, for question 3 is C. So now B becomes constant. Let's see. So the magnitude known the time and again begins to decrease T1 according to the equation. Well, the amount of energy dissipated from T1 to T2 be greater than, less than, or equal to the energy dissipated in part B. Now we know the angle becomes 30 degrees. So from here, the normal vector, the angle between the normal vector and the field, the normal vector and the field, now is also 30 degrees, right? So it becomes smaller. So it will be less than, because delta E is directly proportional to the current, and the current is equal to EMF divided by R. EMF is directly proportional to the magnetic flux. In this case, magnetic flux is smaller because the angle between the field and normal vector is greater. Okay? Then the ring is now mounted on the axial as perpendicular to magnetic field. The magnitude of the magnetic field is now held as a constant, B naught equal to 0.5 Tesla, as shown. The ring rotates about the axle, and the EMF is introduced. EMF epsilon induced in the ring as function of time is shown on the graph. Calculate angular speed of rotating ring in radians per second. So is that constant? Here then the ring rotates by axial in the reduced. Okay, so it looks like it's a constant, right? This is constant. If it's not constant, the graph would not have this shape like that. So if it's constant, I would say, since my flux becomes b times a times cosine theta, and b times a, which is b naught in this case, times cosine omega t. Now let's take the derivative on both sides, right? Epsilon is negative b naught times a d dt of cosine omega t. That should be b naught times a times sine omega t, and based on the chain rule, we need to write an omega here. So we know in this case omega is basically the times b naught times a is the amplitude here of the wave. What is the amplitude? Well, we don't need to know the amplitude. We know we have known the period here. T is equal to, the period is equal to 2 seconds. And we know omega is equal to 2 pi divided by t, which is 2 pi divided by 2 seconds, which is pi radians, which is about per second, which is about 3.14 radians per second. Okay, we need to be quick now. Part E, calculate the magnitude of maximum epsilon max induced in a ring. In the previous part, we know EMF is equal to b naught times a omega times sine omega t. So the maximum value would be b naught times a times omega, which is equal to, well, we know b naught is 0.50 Tesla times a, which is 0.50 meters squared, times omega is pi radians per second. That should be 0.5 times 0.5 times pi. Just 0.79 volts. Now begin rotate at angular speed of 2 omega. What will happen with the change? We need to draw the new graph here. Well, it began to rotate on the, because we have 2 times omega here, so the period would be 2 pi divided by 2 omega, which is equal to pi divided by omega. Well, basically, this is the original period, so T2 is equal to, I would say T2 is equal to 1/2 T, original one. So this is the original T, so T2 would be like this. So we draw a graph like that, right? So this is entire circle will be like this, like that, like that. And since the amplitude should be b naught a times 2 omega, so amplitude is doubles. So amplitude should be at this point. So we need to draw a graph like this. All right. Justify your sketch. Simply identify and addressing any similarities difference between the graph and original graph here. Because when omega doubles t the period halves, and the amplitude should also double. So the newer graph has lower, smaller, shorter periods, and higher amplitude. All right, that's it.